Hi, I'm back. We are going to now move on to Thermochemistry 101. This is part 2 of 2. And what we're discussing right now are heats of reaction. And the heat of reaction is just the heat change that occurs. It's okay. Just put it back up. Heat change that occurs with any chemical equation, chemical reaction. And so the delta means change and RXN means reaction. And so the heat of reaction is just, the heat change that's associated with any chemical reaction. And we communicate with heats of reaction using thermochemical equations. No. So thermochemical equations have a balanced chemical equation with an enthalpy change attached to it. So a really generalized version of a thermochemical equation might show A and B as reactants to make C as a product. And then over here, you're given delta H, and maybe we'll make this an exothermic process of negative 100 kilojoules. So that's a really generalized version. So this is the chemical part, and this is where the thermo part is. So thermochemical equation. Okay, so we're just going to go through a couple of just really quick example here, and we're going to look at the combustion of C2h6 as our example. And I'm going to give this just a really general delta H of negative 1,900 kilojoules, like in that ballpark. Okay, now I would balance this equation, and those coefficients would be 2, 7, 4, and 6. Now what's interesting about this is that I could say for every 2 moles of C2H6, there were 1,900 kilojoules released. Okay, so this is an equivalence that we can use from the balanced chemical equation. I could also say for every 1,900 kilojoules released, there were 2 moles of C2H6 used. And I can do that for any of the reactants or the products. So maybe take a minute and write down an example of an equivalence that you could take from this balanced chemical equation and this delta H. So write one down. I'll wait 30 seconds. Okay, so that was a long 30 seconds. What did you come up with? Let's look at maybe a couple more examples that you could have written down. So we could say, we could use a product. We could say for every 4 moles of CO2, there were 1,900 kilojoules released. Or we could flip that over and say for every 1,900 kilojoules released, there were 4 moles of CO2 produced. Okay, so We can use these equivalents in dimensional analysis. Problems. So let's say that, for example, as an example, we are given if, we'll say 85 grams of CO2 are produced, what is the heat change associated with that? Okay, so we have 85 grams of CO2 being produced, and we want to know what's the heat change associated with that. So the first thing we have to do is take a look at the CO2 and notice that it's given to you in grams and you're asked to answer in kilojoules. So what we're going to do is take our 85 grams of CO2 and then we're going to convert to moles using the molar mass. So we're going to go 1 mole of CO2, and we're going to use the molar mass of CO2 of 44.009 grams. And then we just have one more step. We're going to look back up here at the balanced chemical equation and notice that there are 4 CO2s. So we end up with 4 CO2s. And then negative 1900 kilojoules is the heat change. So what we're trying to do is cancel out grams and moles and get to kilojoules because we're asked to answer in a factor of heat. So we want to look at this and go, okay, well, grams cancel, moles cancel, and we end up with kilojoules. So we're going to break out our trusty calculator and we're going to do the math here, and the math will be 85 times negative 1900, and then divide by 44.009 and divide by 4. So let's see what you get. Okay. And so I get negative 17 kilojoules, and that makes sense with our sig figs too. We've got 3 sig figs here, so we want to answer with 3 sig figs in our answer.
Sig figs.
Sig figs. Significant figures. Can you straighten that out?
I can try.
Okay, so that's an example of a calculation where we're going from grams to kilojoules. And the next example, we're just going to go from kilojoules to grams instead. So I'm going to flip this page. You can come back to it or rewind or whatever you need to do. We are going to continue to use the same equation and the same delta H just for simplification purposes. Okay. I got paper. Okay. So we're going to do, as our second example, we'll say if 3575 kilojoules are released, how many grams of oxygen are used up? So this is an example where we're given the heat factor and we are asked to answer in grams of oxygen. So we want to keep the big picture that, of course, getting to grams always has to come by way of moles, and our ticket to the moles is using one of the equivalents that we just practiced writing. Okay, so we're going to start with our heat, our kilojoules here. we'll have negative 3,575 kilojoules released. And then we're going to go straight to an equivalence factor. Excuse me. We're going to go straight to an equivalence factor where we use the heat of reaction, negative 1900 kilojoules. And we are asked about grams of O2. So we're going to look back up at our balanced chemical equation there and see that there are 7 O2s for every negative 1900 kilojoules. And that is representing in moles. So maybe make a note to yourself that that's moles. And then we can take 1 mole of O2 and we're going to transfer it into grams using the molar mass of the O2. And that's 31.998. And so we'll just break out our calculator again and we will plug in our numbers and chug out the answer. My college teacher always called it to plug and chug. Plug and chug. Okay, so we get, let me just make sure, 3575 times 7 times 31.998 divided by 2. Yep. So this comes out to be 421 grams of O2. Okay, so you can use the thermochemical equation to translate between heat and grams of reactant or product, or you can go from grams of reactant or product to heat released. You can also use this with Pivnert, but we'll get into that another day when we're doing our gases unit. And this is me signing off for Thermochemistry 101. And if you have any questions, you can post it in the comments. And I hope you had a good time watching my first video. Bye.